Hello everyone, this is John Miko, and I'm recording a review of the homework that I assigned you yesterday, which I guess was November 15th. So I'm going to do all the homework problems and on this video, and I'll explain why in my email. So let's look. We are talking in Chapter 7 about continuous probability density functions, and we covered two. One I says, hey, really doesn't matter, and one I said is the most important one that we can learn in the world of statistics. So the first one that doesn't matter except for the concepts that it teaches is the uniform distribution. So number one in your text is that example. It says the weekly output of a steel mill is a uniformly distributed random variable that lies between 110 and 175 metric tons. Compute the probability that the steel mill will produce more than 150 metric tons. So here's what we're going to do. Okay, so first we're going to say, well, this thing is uniformly distributed between 110 and 175 metric tons. So 110 is here, 175 is here, and it's uniform, so it means it's flat. So I drew the picture. Now I want to figure out the function. Well, the function for any uniform probability distribution is 1 over b minus a. So in this case, a is 110, b is 175. So the function is 1 over, let's see, 175 minus 110 gives me 1 over 65. That is the function that defines that distribution from 110 to 175. So the first one, part A, says what is the probability that the steel mill will produce more than 150 metric tons? Well, let's see, 150 is here. We want more, so we want to find the area under the curve greater than 150. The area under the curve represents probability, remember, because it's continuous. That is definitely a rectangle. That's a rectangle that goes from 150 to 175, so it has a base of 25 and a height, because everything has the same height, of 1/65. Multiply those, and I get, hey, there's a 38% chance, 5% chance, that this steel mill produces more than 150 metric tons. B says, how about between 120 and 160? So B says, what's the probability that X is between 120 and 160? Well, let's see, 120 is here, 160 is here. Now it's another rectangle, has a base of 40, a height of 1/65. So 40 times 1/65 gives me 61.5%, or 6.615, however you want to look at it. All very well and good. So that was easy. What if it asks us for the average output? So the average output is A plus B over 2. Because this thing's symmetrical, I just want the midpoint. 110 plus 175 divided by 2 gives me 285 divided by 2. 285 divided by 2 gives me 142.5. So the average output from this steel mill is 142.5 metric tons. If it asked me what the probability was that I produced exactly 142.5 metric tons, hey, because I'm saying exactly, it's kind of a trick, right? Exactly 100 anything is 0 or virtually 0. Let's stick with the same one. What if I asked you what's the probability that I produce more than 100 metric tons? Well, 100 is here. It looks like the whole damn curve is greater than 100. So what part of the curve is greater than 100? All of it, or 100%. Likewise, if I said something like the probability that X is greater than 200 metric tons, well, 200 is here. What part of the curve is greater than 200? Nada, nothing, 0. So as I indicated to you guys, there'll be a problem like this on your final exam. It should be a slam dunk. This is a distribution that isn't used a great deal, but it's used to teach you three things. A, what a probability density function is. B, that we find area under the curve to represent probability, and C, the odds that it takes on any given value for a continuous probability density function is always 0. So that was number 1. Okay. Other ones I'd like to do, let's do number 8 and 9. Okay, let's do number 8 and 9, because 8's a good one. So number 8 on page 116, we are talking about a probability distribution that is continuous. So it says a new gas and electric powered hybrid car has recently hit the market. The distance traveled on 1 gallon of fuel is normally distributed with a mean of 65 miles and a standard deviation of 4 miles. Find the probability of the following events. So let's draw the curve first. And I'm going to try to do this way. So let's zoom out a little bit. Ooh, okay. So we start out by saying, hey, this curve has a mean of 65 and a standard deviation of 4. Remember, 2 things and 2 things only control the shape of the normal curve. The mean controls the middle. Standard deviation controls how spread out it is. If I increase the mean, I shift to the right. If I decrease the mean, I shift to the left. If I decrease the standard deviation, it becomes narrower and more peaked. If I increase it, it becomes more spread out, wider and flatter. Okay, but this one has a mean of 65 and a standard deviation of 4. The first one, part A, says, hey, what's the probability that we get more than 70 miles out of that gallon of gas? Well, we know from the last one that the area under the curve is equal to probability. So this area is equal to that probability. But that's not a nice shape like a rectangle, so I have to find the area, but I don't have a nice formula to do so. Well, what's nice is I have a formula that takes x values and converts them to the standard world of z values. Okay, that formula is z is equal to x minus the mean divided by the standard deviation. So let's do that. Let's convert that x of 70 into a z value. Probability that x is greater than 70 is the same as the probability that z is greater than, let's see, x is 70, my mean is 65, right? That's my mean for my original curve. My standard deviation is 4, boom. So keep going with the math. The probability z is greater than 5 over 4, or the probability that z is greater than 1.25. Okay, so let's draw the z curve. The standard normal curve has a mean of 0 and a standard deviation of 1. And we're saying the odds that on a non-standard curve with a mean of 65 and a standard deviation of 4, the odds that we get more than 70 miles on a gallon of gas is the same as in the standard world that we get more than 1.25, that z is greater than 1.25. So all we've done is translated something we don't know anything about to something we know everything about. How's that? Well, we have a table, which you were given. You'll be given for the exam. Obviously, you don't have to memorize it. And that table gives us all cumulative probabilities. We're looking up 1.25 here. So here's 1.2. We need to go over to 5. And we get 0.8944. But that's area to the left. So if we go back, whoops, there the lights went out. The area to the left is 0.8944, but remember we want greater than, so it would be 1 minus 0.8944, which gives me 0.0956, or 9.56%. Boom. Okay. All right. That is part A. Let's look at part B. The car travels less than 60 miles, okay? So the probability that x is less than 60 miles. So once again, we want to go up here and we want to find the area under the curve less than 60. Well, that's another shape that I don't know. But I can use the same formula to convert that x to a z-value. The probability z is less than 60 minus 65 divided by 4 gives me the probability z is less than negative 1.25. Golden. This is less than. So if it's less than, all I have to do is a lookup. I'm going to find negative 1.2. I'm going to find 0.05. And it gives me 0.1056. Oh, so this one should have been 0.10506 too. Did my math wrong. This is 1056. Thank you. So 10.56. And it makes sense, right? This thing is symmetrical. So if we go over 5 units and then want to go everywhere to the right, we go over 5 units everywhere to the left, it's going to be the same. And then number C, letter C, hopefully we don't run out of space here. C says, hey, how about if x is between 55 and 70? Okay, well, I have two x values, 55 and 70. I need to translate both of them to z-values. So 55 minus my mean, which is 65, divided by my standard deviation, which is 4. 70 minus 65 divided by 4. That gives me the probability that z is between, z is between negative 10, that's negative 2.5, and this is 1.25. So I'm just going to draw a little mini z graph here. We want the odds that it's between 1.25 positive and negative 2.5. So that shape, that's not a shape that we know. But what we can do is if we look up 1.25, which we already did, that gives me 0.8944. So this and down is 0.8944, but that's more than I need. I need to get rid of negative 2.5 and down. Well, let's look that up. Negative 2.5 gives me 0.0062. So minus 0.0062, that gives me 2, that gives me 8, gives me 8, 8. So, excuse me, looks like there is an 88% chance. So this was a good one because it went through all 3 types of lookups. If it's greater than, remember, we do a lookup and we end up subtracting that lookup from 1. That's what we did at the end. If it's less than, I don't know why I started with a greater than sign, but if it's less than, we just do a lookup. We looked up negative 1.25, got our answer. If it's between 2 values, we find the z-values, and then we look up the bigger one, and then subtract out the lookup of the smaller one. So this was number 8, okay, in your book on page 116. Let's do number 9. So that's kind of cool that, you know, the mileage you get on a gallon of gas is normally distributed. We talked about a lot of things that are. Another example is number 9. Can also be how long tires last. So let's do number 9, which is on page 116 as well. It says the top selling red and Voss tire is rated at 70,000 miles, which means nothing. In fact, the distance the tire can run until they wear out is normally distributed random variable with a mean of 82,000 miles and a standard deviation of 6,400 miles. So let's draw that curve. The mean tells us the center, 82,000. The standard deviation is 6,400. Boom, boom. It wants to know what is the probability that a tire wears out before 70,000 miles. Well, let's see. 70,000 is here. This area is equal to that probability. Unfortunately, it's not a nice shape. I need to convert this x value to a z value. using our trusty formula. Z is equal to x minus the mean divided by the standard deviation. Let's use that formula. Probability Z is less than, let's see, 70,000 minus my mean, which is 82,000, divided by my standard deviation, which is 6,400. Let's do the math. Let's see, 7,000 minus 82,000 gives me negative 12,000, divided by 6,400 gives me negative probability that Z is less than negative 1.875. And we want to round it a hundredths place, so probability that Z is less than negative 1.88. The reason we want to round it up the hundredths place is that's what our table goes up to. So this is less than, great. All I have to do is look up negative 1.88. Let's see, negative 1.8 is here. We need to go over to the 8 column. 0.0301 is our answer. So there's about a 3% chance, 0.0301, or a 3.01% chance that we're going to get gypped. We're going to get less than 70,000. What's the odds, though, that we get some bonus miles? What's the odds that we get more than 100,000 miles? That's awesome. We can get more than 100,000 miles. Well, once again, we want to find the area under the curve greater than 100,000. All right, well, let's do that. Let's convert that x value to a z value. 100,000 minus 82,000 divided by 6,400 gives me the probability z is greater than, let's see, that's 18,000 in the numerator divided by 6,400 gives me 2.8125. The probability z is greater than 2.81. Remember, we rounded a hundredths place. Okay, so I want to look up 2.81, but because it's greater than, it's going to be 1 minus what I look up. Let's look up 2.81. 2.8, 01, 0.9975, 0.0025, or 0.25%. So very unlikely. Now what if some crazy dude comes in and he says, hey, what's the odds that I get let's see, what's the odds that I get, I'm going to make this, what's the odds that I get more than 146,000 miles? Okay, so he says, hey, what's the odds that I get more than 146,000 miles? Well, if we think about it, just looking at it, let's see, 82,000 is normal. We've got 3 standard deviations, so that puts us around 100,000. Some dude's asking me, what's the odds he gets more than 146,000, which would be out here. Wow, it doesn't look like it's likely, but let's see. The probability that z is greater than, let's see, 146,000 minus 82,000 divided by 6,400. That gives me 64,000 divided by 6,400. Probability z is greater than 10.0. So you may say, all right, probability z is greater than 10.0. Let's look up 10 on our chart. And we'll notice it only goes up to 3.89. Okay, and it has almost everything, 99.99%. So what do you think? If this goes to 3.89 to negative 3.89, we're looking for the probability that z is greater than 10. What part of the curve do you think is greater than 10? There is something out there, but it's very, very little. So we're just going to say virtually 0. Okay, virtually 0. So that was 8 and 9. 4 and 7, very similar. You want to convert it to a z value, do the lookup, and find your value. So these, there's a system to it, very, very powerful stuff. I'm going to stop there. That's the homework review. I'm going to record another video where I have some new material on here. Have a good day.